So starting the presentation today by Dr. Juan Adrian Ramos Guivar, Universidade Nacional del San Marco. Okay, Juan can start.
Thank you very much. I especially sent to the LACAME committee, especially to Edson, for inviting me to this renowned conference of most power spectroscopy. Some of you know me as Juan, others like Adrian. I also work with Professor Litterst many years in the most power relaxation spectra modulation, and with Edson, Professor Maya Arencibia from Rey Juan Carlos University. She's also an expert in the field of remediation processes. The title of my presentation today will be Functionalized Magnetite Magmite, Applications in Biomedicine and Water Cleaning Processes. First of all, I want to invite you to visit Peru. We have several climates, beautiful, breathtaking views. The Amazon, the center of Lima, has many colonial parks, and you can also visit the Seven Colors Mountains, Puno, Titicaca Lake, of course, Machu Picchu. And we hope that the next location for the LACAME 2024 will be in Peru. So all of you are invited. So the aula for my presentation of today will be focused in the main concern on water demand, specifically focused on around the world, the pollution problem we have in Peru, some of the objectives, synthesis and functionalization methods of nanoparticles, methodologies for treatment of waters and absorption. I will be make really shortly here in the kinetic models and results and discussions about characterization techniques will be the focus of the presentation, together with some acute ecotoxicological properties. Some conclusion and acknowledgements I will present also at the end. So there is an important question. What is the estimated water consumption till 2050? Because we have an increase also of the population every day in the metropolis, specifically in South America. And we don't have environmental conscious awareness about the use of water. Only 2.5% of water is fresh and available here in the planet. 1% is found in underground waters. So it means that we have only 1.5% to be used and treated, and we have to develop a culture to recycle that water, to learn how we can manage that problem with young researchers, young people, specifically youngers, because I see many professors, but too many students, too short students here, right? I see you have to transmit that to young people. Well, here in Peru, we have the problem of pollution. Many rivers, lakes contaminated with, in this case with arsenic and organic pollutants and pathogens that are reducing the living rate in many parts of my country, so affecting the style of life. So the question here is, are we concerned about this problematic in our daily lives? Are we focusing on these problems, or we are just doing nothing to attack this problem? So here, after the problematic was mentioned, we have to say that we have to synthesize the magnetite nanoparticles using co-precipitation method and medium scale. I will say briefly, because we need to use co-precipitation method and not other ones. The development of lead removal protocol from real water using the hybrid nanomaterials made of zeolite 5A and magnetic nanoparticles, some of the optimization of multiparametric absorption parameters, and the evaluation of the ecotoxicological effects and recycling properties of the nanomaterials. So, as you all know here, we have a lot of physical and chemical methods, top-down and bottom-up approaches that we can use to produce nanoparticles. The main problem here is the agglomeration of these particles through physical methods and some of biological methods. So the advantage of chemical methods is that we can obtain high purity, high stoichiometry, and high amounts of the nanoparticles, and we can reduce the agglomeration and flocculation problems using, of course, chemical organic materials. So it's important to define the types of functionalization. We have the ligand exchange and ligand modification approach. We can see in the slide, the ligand modification approach consists you have the initial phase and transfer that phase from a hydrophobic to hydrophilic environment by changing the initial organic functionalization molecule. And we have the ligand modification approach. We can see that we only modify the surface by another chemical group, so forming another second layer. So we have a double layer functionalization, and the goal of this functionalization is to achieve a hydrophilic surface with a high zeta potential that can be applied in many fields, specifically biomedicine and environmental applications. So about methods for water treatment, we have a lot of them: plasma filtration, osmosis, electrolysis, precipitation. Many of them are being used in the industrial applications, but among all of them, we have absorption. Absorption can be very competitive because of the wide range of absorbents that we have available. So we have good absorption capacity, of course. They can be applied for organic and inorganic removal. And the mixture of these magnetic materials forming secondary, binary, ternary, and quaternary magnetic nanohybrids can be also be used for heavy metals removal and other pathogens. So the absorption protocol is very known in the literature. In batch condition, we apply the nanoparticles, certain amount of the nanohybrid to the polluted water as a certain initial concentration of the polluted effluent. And we see the interaction across time. We determine the equilibrium time under certain conditions. And of course, we can take advantage of the specific surface area, the zeta potential, the active site on the surface, and many other parameters that can influence the absorption process, right? And we can also be very selective to absorb arsenic, lead, cadmium, and other heavy metals from water. So I will pass now to the synthesis of the nanoparticles. Here I use iron salts, common iron salts in a high alkaline medium. As you all know here, we use distilled water, preferable. We don't use purified water, medicated water. We don't use that water because it's very expensive in Peru. So we have methods to produce, but it's preferable for a synthesis that is going to be used for environmental approaches to have the water that is coming from very cheaper weights. So we are able to obtain high medium scale nanoparticles. We can produce, in this case, 8 grams of magnetic nanoparticles. I put it that as magnetite. Magma will explain that in brief. We have the second synthesis using zeolites. I use zeolites because they are very known in the literature. They can be good absorbents for many other metals from very long time. People know that. Basically, the zeolites have this structure. It's a cage structure, and the porosity will be very selective depending on the molecule you want to absorb. You can absorb water, hydrogen, and other molecules like heavy metals, of course, but it will depend on the ring size of this zeolite. Why I use zeolite and which proportions, I cannot mention a lot about the procedure because it's under a patent application this year, but I can mention what is the procedure to follow the correct way to prepare magnetic nanohybrids of iron oxide nanoparticles and zeolite. All right, we do before and after synthesis approach. We mix the nanoparticles with zeolite using as a template in the before synthesis to see if they have some effect in the final product, and after synthesis procedure to see if the zeolite mixture with the nanoparticle can also be good absorbed. So we apply conventional X-ray diffraction to the absorbents. We can have a control pure magma here before synthesis. Some zeolite that is a very crystalline system. Actually, it's a mesoporous microcrystalline structure. And we use, in the co-precipitation method, sodium hydroxide, ammonium hydroxide in order to produce magnetic nanoparticles in the presence of zeolite. As we can see here, using sodium hydroxide, we obtain goethite and maghemite, a mixture. And using ammonium, here we see that we have only one phase. So it's really important, but the zeolite phase disappeared. The peak here, the main black peak is not detected here. So what we do after the synthesis is to produce a mechanical mixture under magnetic stirring for 24 hours, and we obtained the composite here of the maghemite and zeolite nanoparticles. And we also can repeat that method very well. Is reproducible synthesis. We have prepared that. We have taken up to 100 grams of this nanohybrid for remediation. But the problem when characterized magnetically is that we can find, of course, fluctuating states, relaxed spectrum here at 300 Kelvin. And we cannot take information about the purity, of course, if this is magnetite or magamite, single phase can also not be determined. I can here make an approach near nitrogen temperature, but I can add, as you know, many components here, and I can overestimate the actual contribution from these sites correctly of the spinel. So low temperature, we can also apply the model, but the broadening is still significant. So I will need another techniques like synchrotron, as Professor Valdemar said yesterday, to unraveling that properties. Of course, we have the problem of a phase transition in nanomagnetite. Here we have a very good paper of Desi, published in 2008, the year that I entered to the university to do my bachelor studies. They were studying the 36 nanometer nanoparticles of nanomagnetite and 9 nanometers nanomagnetite. So at 300 Kelvin, the spectra has the opposite antisymmetric in comparison to bulk magamite shape in lines 1 axis for both sizes, with increment in broadening due to side effects. As we can see here, the broadening is significant, here not. It's a bulk sample. And from the shape of a 300 Kelvin spectrum, we can infer, as a first approximation, the nanoparticles are bigger in mean size because we don't have a collapsed spectrum here. If we have superparametric spectrum, we hope that these 9 nanometers will be collapsed, or at least have intermediate relaxation components, and this is not, this is a block magnetical state. So it's really 9 nanometers. We have to see about this. Of course, below the Berry transition, for example, nitrogen temperature with small sizes, the spectrum looks now as magamite because of the inversion. Here, as you can see. But we have additional components, iron 2 plus and iron 2 plus, as Jean-Marc has marked in his presentation. But the problem here that we have particles with smaller sizes than 10 nanometers is the oxidation that can occur through co-precipitation method, and we cannot control that. At least using inner atmosphere, the surface can oxidize because the organic agents used for functionalization can also affect the chemical surface composition, and we will have a continuous oxidation and of course this we will at the time to perform the absorption experiments, because we will have iron 2 and iron 3 on the surface, which will coordinate with the heavy metal. These are really important thing that we have to take into consideration. So there is a paper from the lab for 2021, 1 year ago, that was published in hydrophobic medium using ferrofluid iron-based approach. And they claim that they have nanomagnetite in the highly stoichiometric with sizes smaller than 10 nanometers. They say that the mean size of the particles are 5 nanometers here, but as we know, we have to be very careful in the size determination, as Jean-Marc also quoted in the first day of the LACAME, because we are not being so analytic at that time. We analyzed the 10 distributions. It's quasi-spherical, it's really spherical, this is really complex, and we need to use a microscopy expert that can determine that and avoid that bias at the time to determine the mean particle size. So till that time, I have not seen a spectrum of 5 nanometers nanomagnetite prepared by co-precipitation. If you have one paper, please, after reading more than 200 papers, I have not found this highly stoichiometric nanomagnetite here of 5 nanometers. So hence, the fit is not so simple. At bullies, as you know, easily have static components of the magnetic field. The hyperfine magnetic field has a characteristic value at room temperature and low temperature as well. And the nanoparticle, of course, will depend on many important parameters. I have tried to summarize from my experience and several studies focusing on the Mossbauer spectroscopy analysis and other techniques, that we have a fluctuating hyperfine magnetic field This behavior is explained using the Morup equation as showed yesterday by Gustavo below the blocking temperature. Of course, the shape of the Mossbauer spectrum is exclusive of the particle size, and the type of the field will depend on the Mossbauer shape spectrum. Temperature smaller than 20 Kelvin is preferable to start to notice a difference between magnetite or maghemite. So we cannot say nothing at room temperature. We can try many models, but this is not correct. It's a mathematical solution, but not physical. So, more importantly, we have the relevance of next physical phenomena that can be also studied using Mossbauer spectroscopy, of course, combined with many techniques like spin canting, spin glass, supermagnetic relaxation, collective magnetic excitation, that was studied by our colleague yesterday, and exchange bias phenomena. Here are some zero-field IR57 Mossbauer measurements from Mossbauer spectrometry. And we analyzed that before synthesis has intermediate relaxation here at the center to mark particle size distribution at 300 Kelvin. And the after synthesis produces highly distributed particles, but bigger than 10 nanometers. At low temperature, thank you, we can see the two sextants can be used to fit the spectrum. It's a bulk sample, almost bulk. And we have here particle that had the 6 Brownian contributions. So from what comes this contribution is not easily to say, and we are at 20 Kelvin. So we need to apply high field, in this case, in field, sorry, IR57 Mossbauer measurements. So it was something we did with Jean-Marc Labs to finally differentiate this problem with nanomagnetite and nanomaghemite coming from years into the community, as I have seen in these last 10 years of studies. So we published that in a review last year that differentiate the importance of this magnetite or maghemite for environmental applications, and this year also because we found that a secondary phase can form and confirm using in field Mossbauer spectroscopy. This phase is goethite, but it's not seen by X-ray diffraction, as I show you in the sample of ammonium co-precipitation. Of course, when we do the after synthesis procedure, when the maghemite was already growth separated from the zeolite independently, we can see that the spectrum has the same trend of the room temperature. Here, as I told you, two sextants can easily be used to fit. And that's as confirmed using here the in-field Mossbauer spectroscopy. So this is the final solution I think we have found. If we have not the possibility to do synchrotron radiation, we can collaborate with colleagues that have in-field Mossbauer measurements. So the repeat sample has the same shape spectrum, the shape Mossbauer spectrum here, as we noticed from the previous one, this one. So it means that we can reproduce the synthesis from the nanoparticles for the pure nanomaghemite. Of course, when we apply this to reverse these nanoparticles as absorbent, and we remove leaf from water, we can obtain also the Mossbauer spectrum, and we now see significant change in the magnetic extraction, as we prove from Kumbasa and Mantaro rivers. So how we know that we have a lead on the surface is because we perform X-ray photoelectron spectroscopy, but due to time, I will not show that. So to confirm that we have particle size distribution homogeneous after the absorption of lead and in agreement with the zero-field Mossbauer spectrometry, so we perform the particle size distribution, and we see that the particles are not bigger than 20 nanometers in agreement with the co-precipitation method, and of course with the control pure nanomagnetite. I will not be too exhausting in the absorption experiments because of time. I want to talk about it, but it's too short time to do that. But I can mention that in one slide. When we perform absorption removal experiments, cinetic and dynamic absorption protocols must be performed. It implies that we have to do a multiparametric analysis, including cinetic equilibrium, removal efficiency, pH, interference, regenerative absorption cycles, real-world experiments, and to analyze the absorbent dose and reproducibility synthesis of the absorbents. This is really important. But what about the lethal doses? We don't know. Each nanoparticle has a different character, depending on the method, as all you know. So here we have a cinetic equilibrium time that we have found is at least 1 hour. The points are triple points here from each time. And we can see that only the magnemite nanoparticles can absorb very well in real waters, where they have other competitive species that can affect the absorption. And it's a very good absorption that can be improved using the zeolite. I'm not showing here the zeolite because of time, but it can be reduced the equilibrium time to less than 1 hour. So, focusing on the lethal dose concentration, we have to apply that into environmental biomarker. In this the invertebrate clados here in the magna is commonly doing that. Of course, we need to do under certain culture conditions. And we apply that in 24 hours neonates of born, because we need to apply the nanoparticles, and we need that these particles be really fastly to remove the heavy metals. We don't want to have the nanoparticles in the river or lakes for a long time, because our nanoparticles will also act as contaminants, and that's not what we want, right? So we do that with 20 individuals for treatment. We make a daily food. We under this radio of light and darkness, 8 to 16 hours here. And of course, we need of some statistics approaches to calculate the lethal dose concentration, the reproduction rate, using T student and other statistical approaches. So we can use here the Probit method. Here's this Probit famous table to obtain the lethal dose concentration under several doses of magnemite nanoparticles. And we see that the lethal dose is about 0.5 milligrams per milliliters, or just grams per liters. And this is important because we have compared this with the dose that absorb more arsenic in our previous work, and it is really near to that value. It's really close. So and this is good because it means that above this concentration, we can kill 50% of the population of the magna. Of course, this is not convenient for our nanoparticles. Talking about some morphological changes, we can analyze the body, the heart, the spine, the antenna of this Daphnia magna, and we can, of course, make these nanoparticles are causing significant changes, statistically speaking. So after 24 hours of exposition, we can see that this nanoparticle has no significant influence based on the P significant value is not more than 5% here. We have here one concentration is smaller than 0.05, but it's not significant to say that we have that value of only one concentration. It should be at all concentrations here. The same happens with body, spin, antenna. We have not seen, in case of antenna, sorry, we have malformation in the antenna key. Here we see that this is healthy, one is a control, malformation is seen because the nanoparticles tend to be over the carapace here, over the exoskeleton of the Daphnia magna, and they try to accumulate. And when some found malformation that we have seen is increased also in the eyesight. We can see it's not significant, but some stressful can be done in the magna. And the other concentration, we get a decrease in the antenna, where the analysis was more significant, statistically speaking. The problem comes with the reproduction rate. If we use higher concentrations, the individuals, after 2 weeks of recuperation, cannot born more individuals. So that reproduction rate is being affected, right? So, but if we are below that lethal dose concentration, we can apply our nanoparticles in a 24-hour exposition. Finally, I want to say that these nanoparticles, after the exoskeleton is molten, here from Daphnia magna, we can recuperate the magnetic nanoparticles. We can, of course, clean them, wash them several times, and make, again, the Mosaur spectrum to notice if we have some several changes in the magnetic structure. And interestingly, we have seen no changes, I show you in the composition of this magnemite, nanomagnemite at 15 Kelvin. So we can storage these nanoparticles for reuse, and we can use them again in a cycle to absorb other heavy metals in water. And this is really important because these nanoparticles here are 7 years old, and we can still using them in a regenerative cycle, cleaning the water, and of course, storage them carefully. So conclusions that are important from this exhaustive research is that the iron oxide nanoparticles, in terms of infimous Bauer Spectrometry can solve the difference between magnetite and magnetite in cases smaller than 10 nanometers, but a system with 10 ml per gram can be enough for water remediation according to our experience. So at the end, is magnetite or magnetite for environmental application. A system of this saturation magnetization will be sufficient to absorb the heavy metals because of the magnetic response. So ecotophysiological applications have to be performed to understand short and long-term applications in real effluents, polluted or not, lethal dose concentrations, and mortality will define a nanoparticle dose for water treatment, and of course, regeneration of the nanoparticle after exposition to the pollutants and biological species is a priority. We cannot apply our nanoparticles without an environmental awareness. We have to think that an open question from future meetings of Mossbauer and other techniques is that we have to think about what is going to happen with our nanoparticles. At the end, they are going to finish in water. So, and what was the purpose? We say at the beginning of this presentation that we have to save water to 2050. We have to learn that. Regenerate water, recycle water, have to be transmitted to our young generations. That consciousness of environmental thinking. Oh, finally, I want to thank you to all my current team of students at San Marcos. We have 10, including doctoral, master students from biology, environmental engineers, and others. Our researchers here that have helped me to form that group at San Marcos, because as we know, here in South America, we have bureaucracy, and it's really difficult to keep a group. We need to be really exhaustive and be really patient and diplomatic in these things. For a scientific network, I really sent to Professor Edson, a really good friend, Professor Jochen, Litterst, Jean-Marc, Marco, Jair, here present, and other professors that have helped me during my career, my mentors, and national scientific networks, Professor Jessica Bendesu from Universidad Nacional del Centro, Professor Jorge Guerra from Católica University, Enrique is a close friend from Instituto de Cultivos Tropicales, and Roberto Salazar from National University Engineering of Lima. Thank you to ProCiencia for help us with the budget. That is not easily to do research projects that can support these investigations, and to nanotech my students, San Marcos University and others important universities that can help during my professional formation and the education of Minister of Peru. Thank you, obrigado, gracias, Cheche. I tried to do it shortly because of the coffee break.
It went a bit fast, but well. And questions? Oh, there. Nice presentation.
Thank you.
Thanks, Juan, for the nice talk. What can you say about the interaction between the zeolite and magnetite in your composite? Is there any connection, or is just a mixture of phases?
We can say that it's a nanocomposite first, but we have to perform X-ray photoelectron spectroscopy to see if there is some interaction between the surface and the bulk zeolite. We have not performed yet, but we are on the way. 0.5 nanometers of the zeolite.
So it's too small for the magnetite to enter.
No, it cannot enter into the pore.
Okay.
Actually, we have done interaction of mesoporous silica with magnemite. In this case, mesoporous silica can be used as a template for the formation of nanoparticles. I will show you here actually the spectral I show here was that system. We use the pores of silica, mesoporous silica, to control the size of the nanoparticles. So nanoparticles enter into the pore and can be homogeneous in the synthesis procedure to obtain fine particles.
Okay. Other
Thank you.
question?
Thank you very much, Juan. Very nice talk. My question is, do you have some advantage if you have more magnetite than magnemite, or the opposite case?
Actually, the problem is to obtain pure nanomagnetite by co-precipitation. That's a problem that I was speaking yesterday with Patricia, because we cannot say we have nanomagnetite easily, and it will depend of the time that the nanoparticle can have, because we can prepare now, but in some days the nanoparticle we can know if this is nanomagnetite or nanomagnemite. It starts to oxidize constantly. So and it be really important in the environmental application.
Thank you.
Many thanks, Juan. Very nice talk. Is there a strategy foreseen for removing the particles in real systems? I mean, at the laboratory scale, it is you have shown that you can do that, but in a river, for instance, or a creek, how would you do that?
We can prepare a reactor for co-precipitation method, and we can check the stoichiometry to obtain high amounts of magnetic nanoparticles. And we can conserve the properties of nanomagnemite mainly.
But so after you make the treatment of the water, how you take out the in the industrial scale? That's industrial scale.
Industrial scale.
Did you think
Is
about?
Jose Rafael here? He's not here.
Yeah, just
We think that magnetic separation will be promising, but we have permanent magnets and of course low field and high field gradients that can be used, but it will depend on the energy employed for that. So permanent magnets can be an option.
Yep. Any question? Any other question?
Any other question?
We
Juan,
have time.
I would like to ask you that you could make a comment, because you have asked several people here about what's the influence from the other contaminants during one adsorption, and probably you thought about this point, and then you make some comment for us, because that's some point that you have studied also.
As I asked yesterday to our chairman, in the interaction with other interference is really important in real waters. We can have phosphorus, but arsenic is a common phase that can be found in water that has the same structure. And in the case of lead, for example, we have many competitives like cadmium divalent, we have copper, and another divalent cationic species. Well, and in this water that we have analyzed, we have cadmium, we have copper, and also we have iron. But interaction with cadmium is really difficult in real waters. It's also a problem that we have because cadmium is acting as an inner heavy metal there. Magma cannot absorb cadmium in water. It's really slow, and many papers have reported that. Maybe by functionalizing the surface, we can absorb cadmium. There are actually very reports of that, but we need to prove in real effluent. We have to collect, we have to do our work. We have to go to rivers and collect correctly the water, right? We need to worry our society problems, how to do science for our society.
Oh, any more questions? Or oh,
Thank you very much.
okay. Okay. Gustavo.
Still have time. Today is relaxing.
Yeah. Besides being.
Thank you for this very nice talk. Now I have one small question, and it was surprising because of the bags. These bags absorbs in the ice. There is some absorption of nanoparticles.
The
magma. I saw.
So when you have studied
The biological impact.
Daphne Magna.
Yes.
I understand. We say that gorditas. Le decimos en español.
gorditas, no.
Son gorditas. De cariño. In the ice, no, it can be cause some stress, but it's not significant, as we can see here. In the eye, we have no significant p-values to say that all concentration have a morphological change.
Thank you. Nice talk, Juan. Uh, uh, I just wonder if you have done any type of speciation study with the metals that you are being that are being removed, meaning the chemical form in which they are may be important.
Yes, we have performed the iron leaching studies, because we can absorb the nanoparticles, but some iron can be leached into water. And we have to be really worried about it, but it can be controlled with magnetic decantation. The magnetic separation can be really good when we are working with iron nanoparticles to avoid leaching. Mhm. Ah, actually, we will need, in this case, to see that we have a complex between arsenic and iron at the surface, and new complexes will be really interesting. We have done X-ray and photoelectron spectroscopy measurements, and we are under study of that formation of complexes. Very good question.
Any more questions?
Actually, synchrotron radiation can have that.
Yeah. Yeah, there are some studies about using the residue from mineration, for instance, to produce ferrites. Then you,
Rates can be
yeah,
yeah, we don't mention, we don't work a lot with rates because of Virender K. Sharma already do that from Texas University. I don't want to repeat that, but this is so interesting because in collaboration, I read that papers years ago, some of the publications of him. He has worked with Boril from Czech Republic using infamous Bauer spectroscopy. They have seen that high spin states can favorite also the arsenic absorption through cationic changes.
yeah.
It's really important.
But I was giving an example because sometimes what you take out of the water can be used to produce a new product.
Yes.
Okay, it happens. But anyway,
Oh,
Yeah.
great.
Well, as you see, it's not at the moment. It's a very warm day, but nevertheless, it's enough to have a pullover.
Oh, really? Okay.
Especially, I'm afraid poor Camilla will suffer from it.
Uh,
But she should be happy since I think, in principle, it should be at least 5, if not 10 degrees lower than it is by now.
okay.
Okay, let's return to the presentation, I'd say.
Yeah, please.
Yeah.
So let's start now. Let's try, no? So thank you very much, Professor Johan, to be with us. So Professor Johan, for those that don't know him, we have some new student here. He's emeritus professor from Technische Universität de Braunschweig. Oh, de Braunschweig não dá, né? De Braunschweig. So he's going to talk about quantum spin liquids. What can we learn from Mossbauer spectroscopy and muon spin rotation / relaxation? That's it, Johan. If you can, go ahead. Thank you very much. Can you put in presentation mode? It's not in the presentation mode.
It is?
And the red the symbol that I showed you before is in the top, in the bottom. Yeah, that's it.
Is it there? Okay.
Not yet.
No.
No.
Oh, beware. What's happened? I close it once more.
Yeah. Yeah, you have, as we did before, so you have to stop your presentation, and then we have to...
Then I re-enter, sure.
Yeah, that's
I'll
it.
do that,
yeah, you have to interrupt your sharing of screen sharing.
Yeah, well, one moment. Okay. Now.
Yeah, so, ignorar. You have to ignore
Moment.
Okay, that's fine.
It's there? You can
It's
see?
there. It's there.
Okay.
Thank you.
Now I have to restart it completely. Okay. So, bom dia a todos. Desculpe, mas prefiro fazer a apresentação em inglês. Good morning, everybody. I would first like to thank the board and the committee and especially the organizers for having invited me for this meeting. Traditionally, I would have liked to be there, and I would have really have honestly preferred to meet you all in vivo, but as you know, sometimes health doesn't play as we want, and I couldn't travel as I once. What I want to do now, I want to present you a short introduction to spin liquids in general, not only to quantum spin liquids, despite the emphasis would be on that. Then I will give some review on earlier work of us on spin liquids using Moscow effect and MUSR. And finally, we'll summarize some recent and ongoing work together, especially with Elisa's group. So that's actually not the presentation. Okay, it doesn't matter. We have, as you know, several states of matter. You know what a liquid is. There we do not have fixed positions of atoms. They move more or less freely. For sure, we do have some kind of viscosity. But we may, with a lower temperature, we will have a phase transition, and we normally would go to some crystalline solid state, or with some fixed positions, which are for sure dependent on chemical bonding, and that will determine crystal structure. Or, however, if we cool down, we may also through a glass transition and go to a kind of non-crystalline solid, a glassy state. The reason for that is mostly a kind of frustration that occurs due to unsatisfied geometrical conditions for certain chemical bonding which are necessary to form the crystalline state. There are, however, also very rare cases where we can go on down to lowest temperature and have a ground state that persists even to 0 temperature. But at least nowadays, that's even part of physics classes. At my time, that was just when I was studying, that was newly recognized that these states may exist. It's quantum states which occur in helium-3, for instance, and helium-4. It's quantum liquids. The reason for that is that quantum statistics and together with that quantum fluctuations. Let's turn to the magnetic phases. Well, in the magnetic phases, we start out at high temperature with paramagnets which have fast fluctuating spins. Then we go through phase transitions either to ferromagnetic order or to antiferromagnetic order, where this may have a lot of very exotic differentiations, just depending on nearest neighbor interactions. And that occurs all through very well-defined phase transitions at the Curie or the near temperature. What happens if we introduce now frustration? That can come from contradictory informations from nearest neighbor couplings, for instance, or from defects. That may occur that we do not have very well-defined transitions. At least nothing will happen if we pass the typical temperature which corresponds to magnetic interactions, like the Curie-Weiss temperature. And we know that all, then the spins which are fluctuating fast at high temperature will slow down, and they may freeze to a spin glassy state. Well, ideally it will be statically frozen, but usually there's some relic of slow fluctuations. However, there's another possibility. There's no transition at all, and you may go down to zero temperature, and you will end up in the pendant to the quantum liquid we had seen before in structure to a quantum spin liquid. And we still have fast spin fluctuations down to zero temperature. So, who are typical candidates for such situations with frustration in solids? That's typically triangular lattices or tetrahedral coordinations, like on the right, as you see in the superfluous structure, or in the Kagome lattice, which is consisting of interlinked triangles. That's well known. That's the typical candidates for spin gases. We know very well, but they may also be the candidates for spin liquids. Now, what is a kind of a classical spin liquid? A classical spin liquid may, for instance, be a structure which is called spin ice. What is that? Typical examples are these compounds you see here, this dysprosium 2 titanium 207 or the holmium compound as well. There we have F electrons that are sitting with their spins on a paracross structure, on these tetrahedral structures, as you see, for instance, below here. The interaction there is, in principle, from nearest neighbor to nearest neighbor, that's ferromagnetic. But the dominant interaction you have to face here, since you have very large spins and large moments, that's a dipolar interaction, which is long range. However, this interaction will be frustrated since locally there are easy access for these easing spins, and they are looking inside or outside of these tetrahedra. And for sure, there's many possibilities to arrange that, so you will end up in a highly degenerate spin ground state, with spin pairs pointing in or out of these tetrahedra. And that reminds, in analogy, to the structure of a true water ice. From there, the name comes. There you have proton positions arranged in a similar way, regular way, and therefore here comes the name of a spin liquid, which is in this case a spin ice. Now, I had said before, at low temperature, the spins should not freeze and they should stay fluctuating down to T equals 0. That's not the case here. The reason is you have large spins, and these large spins have large walls between in fluctuating between the different configurations. So finally, if you go down to low temperature, it finally will freeze. So it's not a true spin liquid in that definition as we had defined before. There's other examples where we find highly suppressed magnetic order, means suppressed order. If you go down below the Curie-Weiss temperature, you cannot see that the spins will really end up in magnetic order. Typical case for that's the so-called A-type magnetic spinels. Spinels, you know, that's cubic structure, and the substructures are in that way. That's the A site, that's tetrahedral, and that's occupied in this case by divalent iron, as sitting on a diamond lattice. And that's the red tetrahedra here. You see, they are not directly connected. They're interconnected by the pyrochlore lattice of the B sites, which are octahedral. So we have a very weak coupling between the tetrahedral sites, which contain the magnetic ions. All these materials, I must emphasize, are electrically insulating, so it's no itinerant magnets or somewhat like that. I will discuss two cases briefly below that, iron aluminate and the iron scandium sulfide. Now, what is finally a quantum spin liquid? Also magnetic insulators, at least as it is known by now. There we have absence of magnetic order of interacting spins below the Curie-Weiss temperature down to very, very low temperature. The reason there is that we have to face here a quantum effect. We have long-range quantum entanglement, and that for sure is of high applicational interest. It's at least speculated one may use it for quantum computing devices. There's a lot of exotic excitations you may have in these systems. One interpretation about the interaction and why the state is formed comes from that was proposed that it's coming from a superposition of valence bond states in a resonant way, so-called resonant valence bond states. These are entangled valence bond doublets of spin 1/2, as it is described here, spin up, spin down, spin down and up, that's entangled, but many of them are distributed on, for instance, on a frustrated lattice, on a triangular lattice, as you see here. Now, the resonant valence bond state is that you have a really combination of many configurations of all possibly thinkable of configurations where the orientations of these cigars are different from point to point. Now, that works nicely with spin 1/2. But you can imagine if you have larger spin, you cannot really easily combine that to a state of this kind. So that's an example of that. There's many examples of that. It's a good dozen of them which exist by now. Most of them are on triangular lattice, not on square lattice or somewhat like that. That's very rare. So summarize, what do we know by now? There's a huge amount of theoretical work, you can imagine, speculating what may happen. Minor experimental, most effective, I must say, that's neutron scattering, especially inelastic scattering. There you can look for these typical liquid-like excitations. There's few MIRSR and also NMR experiments, NMR on copper, for instance. Still less Mersbohr, nearly no Mersbohr spectroscopy. So I wanted to look and said what we can see at all. Now, let's turn to the MIRSR. MIRSR, as you know, that's the interstitial probes. The muon is implanted in between the atoms, so it will be a spectator of its surrounding. So it will be sensitive whether the surrounding is ordered or whether it's fluctuating, and then it will reflect at which frequencies these fluctuations take place. That's typically between 10 to the 4 and 10 to the 11, second to the -1. So relatively slow in comparison to the neutrons. Now, the Mersbohr side, I need not tell you, know your best. We are probing at the lattice position. Now, the question is now, is the Mersbohr atom participating in the spin liquid? Hardly, since usually Mersbohr atoms have a relatively large spin. Iron, for instance, 3/2, 5, or sometimes seldomly 1/2, but in very, well, you know, the low spin conditions, but in very rare cases only. But you may use it as a spectator in looking to the surrounding. There, for sure, we are also sensitive to the magnetic order. Here we are sensitive to spin dynamics, which is similar to the MIRSR, but it depends strongly, however, which hyperfine interaction you are looking at. For sure, we have here isomer shift and also quadrupolar interaction, which doesn't exist in the muon case. The big problem we face here is really if we introduce an extra Mersbohr atom, it may severely disturb in its surroundings the spin liquid. One has to think about that. And another handicap, especially nowadays, in earlier times it was a bit easier. We have to go to very low temperature. And honestly, I do not know any place anymore who is actively working in lab with 10 to 100 millikelvin range. That would be the interesting surrounding where we would really could trace directly the spin liquid properties. So let me go back to that here. I only want to show you where from the muons, for those who are not so familiar with the method, if we implant a muon has a spin 1/2, and inside the magnetic fields, the spin will start precessing. If it's sitting in the field, it may be its internal field, if it were magnetically ordered, and that's detected if we implant polarized muons, and the polarization of the muons will change with time. That's these oscillations which you see here in the magnetic state. That's detected by an angular correlation experiment. If you are not magnetic, you simply will see a simple damping. And the damping, that's reflecting the spin fluctuations, and especially the spin fluctuation frequencies. The stronger it's damped, the lower are the spin correlations. And with that, we can probe if a material is slowing down or speeding up in the fluctuation frequencies of the spins. Let me turn to this example I had promised, iron scandium sulfide. It has been studied several times before. Indeed, it shows no magnetic order. If you look for magnetization, it has a Curie-Weiss temperature, which shows that we have magnetic interactions, but we only see slight deviations at low temperature. From that, it's non-magnetic. From crystalline electric field, we know, since we have tetrahedral iron 2 in this case, we have orbital ground state of E-type, it's a doublet. And this is the antellar-active, so we can have spontaneous splitting of that. It will be, normally it will be dynamic. The spin of is a spin, not the orbital momentum. The orbital momentum is also 2, but the spin is also in this case 2. Such cases, I want to recommend you to go sometimes back in literature, was nicely treated by François Hartmann-Vautrin already in 1968. I will give you afterwards the citations, and you should look to that. It's very nicely derived there. Nowadays, such papers are unfortunately sometimes lost. There's Nussbauer studies on this material. A very famous one is by Brossard and company. It was presented on one of the Nussbauer LACAME conferences in Corfu. I'm afraid Elisa and I are the only ones in the present conference who had attended that conference. It was a very nice conference. It was introduced by whom? By Jacques Donon. So it was also, I think, very essential on this conference. Jacques Donon decided Elisa start up, which a method we had also in Munich, that was matrix isolation. And she should start with an installation to be built up in her lab at CBBF. So that was essential part of our long years lasting collaboration. Now, back to iron scandium sulfide. What did he see? Sorry, the picture on the left, spectra are very bad to see, but that's, I checked once against the original, it's not much better. You see, at high temperature, you think that it's non-magnetic. And if you go lower, it's broadening. Well, below 80 Kelvin, interpretation of Brossard was that that's developing of several quadrupole interactions due to local disorder, due to local distortions, which come along because of this peculiar state of the orbital state. Now, his conclusion was that comes by random strain, and this will come in by second order spin orbit coupling. And his interpretation was there's no magnetic hyperfine splitting, but it's several doublet patterns. But he was wondering, since the quadrupole splitting was far too big and he could not really relate it somehow to the antenna effect. Now, some years later, it was again studied now by neutron diffractions by the group of Leudler in Augsburg. And they found out, in fact, at least they claim, it is a degenerate orbital state. However, what you have there, it has liquid-like dynamics if we go to low temperatures. So here the case is that it's not only the spin, it's the spin coupled to the orbital state. So it's a spin orbital liquid. And that's close to a quantum critical point. And their fluctuations are fast, and therefore you don't see magnetism. Now, we have again looked to that. There's some, just after that, there was Muir's-R experiment. Actually, one doesn't see magnetic order, but notably below 80 Kelvin, there was found it was two signals. One was fast relaxing, one was slow relaxing. Slow relaxing means we have a slowing down of magnetic correlations. So we have a mixture of two scenarios. We have here, in part, we have fluctuation rates which are relatively slow in the range of 100 megahertz, even at lowest temperatures. And the other part is fluctuating fast. So we have a kind of separation within the material. It comes from inherent, not impurities, but inherent distortions, inhomogeneity in the system, that part of the iron may perhaps occupy B states instead of A sites. These experiments were initiated, actually, I want to remind you of Mike Calvius. Unfortunately, you know, also perhaps he was one of the essential people founding the application of Morse power spectroscopy. Unfortunately, he passed away nearly exactly 1 year ago. I'm very sorry for that, since he was teaching me not only Morse power spectroscopy, which in part I also had together with Morse power himself, but also Muir's-R. We repeated on better samples now Morse power experiments after that, and you see, well, it looks very similar to that what Bosar had seen, but these big splittings we interpret now after knowing about the muon experiments that must be magnetic. What we make, we have an analysis which is composed of a non-magnetic doublet, fast fluctuating, and one broadened magnetic pattern. Now it had temperatures that were already collapsed to a broad singlet level, as you see here. We still have some problems here, so that may be some impurities, but you see the fits work quite nicely here at low temperature. It's now also a combination of magnetic and non-magnetic. So it's separate, as we see also in the muons. The magnetic pattern will have a saturation at a very low field only. That's actually explained by a paper of Feiner already in 82, who explained that in a Jan Teller system, the fields may be dramatically reduced, therefore we only see a small field. So the crossable interaction, what had been before been drawn and explained by distortions, now in reality, that's slowed down dynamic magnetic patterns in the spin fluctuations in the range between 100 and 10 megahertz. So both Muir's-R and Morse power will see a separation into contribution with fast and slow spin fluctuations. Now, the other A-type spinel system I wanted to show you that is illuminate. Also here we will see it's a spin liquid system which doesn't show real magnetic order at low temperature, but we have a separation in fast and slower relaxing parts. Here you see the Morse power pattern, you see the non-magnetic part, and you see a slowly relaxing magnetic part. If we go to the muons at high temperature, once again you see two contributions, one fast fluctuating and one slow fluctuating, and a saturation in fluctuation frequency if you go to low state. So it's not a completely freely fluctuating system, it's slowly fluctuating, but it persists. From the muon side, we can see that down to 25 millikelvin, for sure not with the Morse power part, and that's indicating we are kind of spin liquid state. Here comes the neutron data also, which are consistent with also our data, high temperature paramagnetic, some what is called cooperative paramagnetic, strongly correlated paramagnetic state, and below here, below about 20 Kelvin, or no, 15 Kelvin, we switch over to a dominantly spin liquid phase and a kind of spin glassy phase. Notably, if you disturb this system with a little bit of iron that is sitting on B sites, that's happening here. You have added more irons that can go not only to the tetrahedral, but also to the octahedral sites, only a few percent, you immediately switch over to a ferromagnetic state. So it's very, very sensitive. So the spin liquid state is a very delicate phase. And as we had seen before, also with this tantalum compound, it depends crucially how well defined are the proportions sitting on different lattice sites. Now, let me turn to the work which is still ongoing and the project that's running in a cooperation between Deutsche Forschungsgemeinschaft and FAPERJ. It's running mainly initiated by Lisa in her lab. We are studying a spin liquid-like state in a spin 1/2 square lattice. So here, this geometrical frustration as we had before does not happen. It must be somewhat else since we are sitting on a square lattice. It was a study of structure-specific heat, magnetization, neutron scattering together with muon spin rotation. So that's a publication which came out of it very nice. We had been very happy with Nature Communications. Now, the structure, you see, that's a double perovskite. The major ingredient, that's the copper, that's the magnetic part of it. The copper that's sitting here on the blue side. So the main motif, that's a square we have here. The blue ones, the rest, that's tellurium, respectively, tungsten. Now, electrical insulator again. What's interesting in that system, if you take the pure system, if you go to the pure tellurium system, that's X equal 1 in the structure, you will have a dominant nearest neighbor interaction, antiferromagnetic. Up or to the right, to the left, to the right, to the left, to the left. So that's dominant. The next nearest interaction, that's J2, that would be across here. That's small against J1, which is this interaction. Now, if you go to the other side, to the tungsten compound, it's just the opposite. There we have a dominant next nearest interaction, and this will result in a so-called columnar antiferromagnetic. Here, these two are in one direction, these two are in the other direction. Why is that so different? That comes from a different kind of hybridization. The tellurium states don't hybridize with oxygen, whereas the tungsten, they do hybridize. So now the idea for sure is that what happens then if we mix the two and we are just in between? Then the two interactions become of comparable size, J2 to J1, maybe 1 to 1, and then there should happen frustration. What's happening then? Now, for sure, that's now a question that reminds in the problematics of the cuprate high disease. There we also have square lattices, and you also will remember Phil Anderson's famous paper from '87, where he proposed that there's a possible quantum state in this copper cuprates is a quantum spin liquid on a square lattice. That's exactly our speculations also we had hoped to find here. Now, what did we find? We made MUSR at Pauschere Institute in Switzerland, and for sure, then I wouldn't show it to you, we don't see magnetic order down to 19 millikelvin for the 0.5 compound. That's just sitting between the opposite cases, between the columnar and the normal antiferromagnetic. What we see also, you see that's the damping of the muon sinker. If you go down in temperatures, the damping becomes stronger. Stronger damping means the magnetic correlations are getting stronger. The fluctuation frequencies are slowing down. It's plotted down here. That only follows the red curve here. That's a logarithmic scale. You have a slowing down here at high temperature, but then below 1 Kelvin, it's suddenly turning out and saturating down to low temperature. So these fluctuation frequencies, which are on the order of some 100 megahertz, they persist to lowest temperature. Typical signature of the spin liquid. In this case, it's indeed a quantum effect since we see it only at very low temperature. The Curie-Weiss temperature actually is around 50 to 80 degrees. much, much higher. So we could derive a phase diagram of that. We found no order actually over, not only at 0.5, but over a wider range extending here, just in the middle of this gap between the tellurium and the tungsten compound. That this is not going down to zero. That's the only reason we didn't get beam time for this low temperature equipment. So our lowest temperature was only 1.5 Kelvin. It was only suspicion that it stays down like it does for the 0.5. In the border regions, we find still order extending here, down here to even 0.6. On the other side, it's very narrow. It's very close to the tellurium compound that with mixing in tungsten that we already lose magnetic order. So the reason for that now is nowadays from much more recent experiments on that and theory, this comes from random spin singlet formation in this area in there. And for sure, we have disorder here just from the mixing of the two compounds. So it's not only at one concentration where we have frustration, but over a larger range. So the newest phase diagram looks like that. That's our data. Our data also, it claims that there is some kind of short range order which extends over here to higher concentration and here in the middle, as we know already, as we found already here. There is no order at all, and we're really in a spin liquid state. That's the paper just recently appeared about the suppression of this antiferromagnetic order in a two-dimensional random quantum magnet. That these valence bond states I had initiated just before. Well, we had some doubts about that here. So we decided to look once more to the border conditions. That's x equal 1, the one on the tungsten side, on the tungsten side, and x equals 0 on the tellurium side. The tungsten side I had showed you before. We see nice order at low temperature with a well-defined ordering temperature. But if we look on the tellurium compound, we do not see explicit order. We see some fluctuations here, but what we find is only 20% that is ordered. The rest actually is spin glassy with slowing down fluctuations. So that's not a proper antiferromagnet. Now we'll say, yeah, it was claimed before, yes, there are neutron scattering it, and the neutron scattering these very nice magnetic reflexes. It's an antiferromagnet. Here, from the muons, we see partial order and partial spin glassy dynamics. Now the ordered part, that follows a nice magnetization curve in frequency that corresponds to the local field, which is quite normal. But why is this superposition? Is there a contradiction? Well, we have to keep in mind that neutrons and muons see somewhat different. So the time-sensitive windows are different. Elastic neutron scattering is fast. Here we are relatively slow with the muons. We are on the range of microseconds to nanoseconds. Here we are below 10 to the minus 12 with the neutrons. Therefore, it's no contradiction at all. Simply, the neutrons cannot see this slow dynamics if you are in elastic neutron scattering. One should look for inelastic neutron scattering. So what does it mean for the interpretation that we see this superposition? That gives a hint that these spin singlets are not only happening, appearing in this frustrated relation in between the two compounds, but even in part, even in the antiferromagnetic range for x equals 0. So it's extending into the antiferromagnetic range. So now you will ask, where's Nussbauer spectroscopy to come to the end? There is, in fact, a possibility to introduce iron into this compound. Well, Elisa had proposed that, Cynthia had tried it together with Sami, and actually, I must say, to make it short, it works. for sure you cannot introduce iron by itself into copper, so you will get some misfit from charges, so you have to compensate it. So the way it's done is that you compensate with introducing some trivalent antimony. This is a tellurium here, and in this way you can compensate for the charges. From X-ray, we can see that the structure is kept nicely. Now, if you look for the magnetic data, here you see magnetization susceptibilities. Here you see the undoped, that's a typical bump for the onset of the magnetic correlations. That's a pure compound, so it's for 0.5 and 0.5, as we had before. We had this complete suppression of magnetic order. Here, that can come from some paramagnetic impurities that are left. Now, if we dope with iron, only with low concentration, well, in principle, you see still this bump here in zero field couplings that looks very similar. The scale here, the vertical scale is different, therefore it looks also different. But the essential point is that on field cooling and zero field cooling, you see deviations that you don't see here. So here, somewhat is happening. Well, it's easily explained. Well, if you dope in iron, you may have in part small correlated clusters. It may be small iron clusters that are somehow formed. Which kinds they are, we still do not yet know. But in principle, at least in zero field cooling, it looks very, very similar to the clean compound. Now, how does the mass power spectra look at? That's actually not done with 0.5%, it's done with 5% of iron. With 0.5%, we should have worked with enriched iron, and that was done with unenriched. You see, nice patterns, nice doublet pattern at high temperature. In going to low temperature, you see some onset of some magnetic background. That's there where you have where we see also the onset of correlations just in magnetization. At lower temperatures, that develops to well-defined, not well-defined, clear sextets which are horribly broadened. And in addition, sorry, where we are, here we are. And in addition, what we see says develop, there's changing here in the states here, we have some extra line, that's some divalent contribution, which is back there, that's smeared out. And we have, in addition, if you look just for the asymmetry here of the lines, it goes to the other side completely if you go to low temperatures. And you have an additional pattern in there, which is slowly relaxing. It's not the fully developed field as we see for the cluster, but it's gradually growing on expense of the doublet. The doublet is still non-magnetic down to lowest temperature, but we have the onset of magnetic correlations. And that's actually what we see also in the muons. In the muons for this compound, we see an onset of the slowing down of correlations below about 5 Kelvin. That's exactly seen here also. So what does it mean? We have here also the possibility by introducing iron as a spectator to monitor the slowing down of the spins in the matrix. So the spin fluctuations are the order of 10 to 100 megahertz. That's very similar to that what we see with the muons. So that gives us a possibility now also to look on such a quantum spin liquid by means of mass power spectroscopy. Yeah, unfortunately, I told you before, we can see only the start of this slowing down at 5 Kelvin and 3 Kelvin, but we cannot go lower. So what should go far lower? So that means we need further studies. So my proposition in this case, why isn't it perhaps possible to introduce not iron, which tends to cluster, and for what you have already these strong correlations at higher temperatures, why not put in a non-magnetic spectator like tin? Dalbert spoke about that some days ago. I think it's more or less some kind of lost isotope, which I think is very valuable. So one has to try whether one cannot look at that. It's non-magnetic, it shouldn't disturb the spin liquid. and we can directly see from transferred fields how the correlations are developing. To summarize, I think on local scale, it is really a good combination to look at mass spectroscopy together with MUSR on the same samples. We can have insights, especially to the mechanisms which lead to very different kinds of spin liquid behavior, as we had shown before, for these classical spin liquids or the orbital spin liquids, and now also on the quantum spin liquids. Where I think is the special strength is that we can trace intrinsic inhomogeneities, which are close to a quantum critical point. That is the case, for instance, in the iron scandium sulfide, and also now in the latter case with the strontium copper double perovskite, where it's also suspected there is a quantum critical point just between the two different opposing magnetic orders, where they are most competing, and therefore, in this way, the local correlations are not dominated by the local exchange alone. So now I want to thank especially all my collaborating colleagues, especially those from CPPF, and there especially for sure Elisa. At this point, I must say I'm very sorry that she cannot be anymore at this conference. I just had a mail from her before that she has to leave. I have been collaborating with her now since nearly 50 years, and I think it was always very enchanting and very successful to work with her and with all those Latin American colleagues I could meet during my stays at CVPF. And I think to all my friends, all the best, and have good ideas what will happen in future. You keep in mind that Moskva's spectroscopy, despite sometimes suspected in international community, is still alive and may give very valuable input, both to applications as you saw with the nanos before, but also to basic science, as I hope I could show you. Muito obrigado, and thanks for your attention.
Thanks so much, Johan. Thanks so much. So time now is open for question. Yeah. Time is open for question. Julian.
Hi, Jochen. Many thanks for your talk. It was very interesting. As always, your talks are very interesting. I just have I don't know if it's a silly question, but when you talked about this iron scandium sulfide, you say that it is close to a quantum critical point, right?
Yeah.
So, the
competition, it's a bit between, you have an extreme strength of spin orbit coupling there on one side, and on the other side, with whom we are competing, that's just the antiferromagnetic exchange. And if the both are coming close in strength together, then you will have a quantum critical point. That's predicted from theory.
Okay, so my question was if you can extract the signature of the quantum critical behavior from Mossbauer spectroscopy, or from MUSR, I think that is much more plausible. But from Mossbauer spectroscopy, I don't remember I have seen any work regarding, showing like a signature of quantum criticality. Maybe you can answer that to me.
Difficult. No, I think honestly, quantum criticality has to come is much easier to see from MUSR. Well, in the Mossbauer case, it's like also with all these liquid states. What you see typically on the Mossbauer side is that there's absence of order. Absence of order. What that will mean? You are in a fast fluctuating regimes. That means your hyperfine interactions are averaged out in the fast limit. And therefore you only see a singlet or a doublet. And to see the critical fluctuations, then you would really have to analyze in a very clean sample, in a very, very careful way, line broadenings. And that's, I think, very, very difficult. And in most cases, these effects are overwhelmed simply by inhomogeneous broadening of your resonance lines. So it would be very, very difficult.
Some other question? No? I have one, Johan. So can you make a comment for us? For example, suppose that you don't have mu-NCR, okay, experiment. You only have Mossbauer experiment, but you can go to low temperature, and in some cases you can apply a magnetic field. So my question is, if you take this scandium system where you have shown the spectra, so the spectra, they have a very small magnetic hyperfine field. How do you distinguish between the magnetic hyperfine field from the blocked state where your magnetic moment or your hyperfine field is quite small from those that come from the relaxation process?
Only by systematics of this temperature. Well, in this case, the broadening persists if you go below 20 Kelvin. The broadening persists if you would be in a spin gassy state, or you would be simply, or let's say a superparamagnetic state where that is slowing down. Take just those examples what Juan had shown before with clusters or small particles. There you should have a narrowing if you go to low temperature. Here you will really maintain broadenings down to lowest temperature. Then you will say, nevertheless, there can be disorder in homogeneous broadening. Yeah. I admit. With that, I think there you can look with applied field. That's actually still missing with the scandium sulfide. Yeah. At this time, when we made these measurements, our magnet cluster was not operating. So we should repeat that. I think that's very essential to distinguish between inhomogeneous broadening and relaxation. But that's a basic problem you have always with Mossbauer spectroscopy. That can indeed be done much easier with MIRN spin relaxation, where you can directly distinguish between static broadenings and dynamic broadenings.
Okay, thank you. Any other question? If not, we thanks again, Johan. Thank you very much.
Thank you.
And now we are going to move to Magda Bittencourt from CBPF. She's going to tell us 57 iron Mossbauer stud on the cerium, ruthenium, germanium too.
So thank you, everybody. I would like to thank the organizing committee, especially Edson, that gave me this opportunity to talk about a very simple work. I'm not a specialist in Mossbauer, despite I'm responsible for the Mossbauer lab in CBPF nowadays. Elisa is still our scientific leader, but for bureaucratic things, I'm now have this responsibility. So I'm trying to go inside the field, but I'm still not very, let's say, I'm not from the field, I would say. So I would like to talk about this system, and these are my collaborators. These are my collaborators from the very beginning of these studies. I studied this material in my PhD thesis, and now I'm collaborating mostly with Mariela and Dauber, because we are trying to finish a work we started a long time ago, and it was abandoned for some reason. And then since I gave to my students 2 years ago, and we decided to finish this and publish sometime, I hope. And this is CBPF. It is located in Urca, in Rio de Janeiro. It's a very pleasant place, and I would like to show you this, and everybody is welcome to CBPF if you want to go there sometime. Here is the beach, and here is CBPF, this nice building here. So I think is this. The outline of my talk is just an introduction. I will show you some facilities there and some examples of the work we do in CBPF in our group. Some brief introduction of the material and motivation, result discussions, and conclusion. Okay, since I told you I'm not from specialist in multiball spectroscopy, my field of research is in strongly correlated materials, okay, in strongly correlated electron systems. And just for the people who are not from the field, non-interacting electron systems, a system whose properties are easily explained by simple theories, and which the electronic correlations can be neglected, like in normal metals like copper, aluminum, gold, etc. Okay, and is well explained by band model, and that successfully described the metals, insulators, and semiconductors. But in strong correlated systems, these simple theories cannot be used, cannot describe these systems. And bigger discrepancies may occur at low temperatures where the thermal energy is greatly reduced. Okay? New complex phenomena arises from these correlations, and we can exemplify by the high-C superconductors, heavy fermions, multi-insulators, multiferroics, and many systems with very, let's say, exotic behavior compared with normal metals, of course. So the heavy fermion systems are compounds, in general intermetallic compounds, formed by atoms with unstable F shell, and also with some transition metal, or maybe germanium, tin, silicon, and this kind of material. You can find a strong competition between the Rudman, Kittel, Kazuo, Yoshida interactions that competes with the Kondo effect, okay? And in general, they present a phase diagram that is show here the competition between Kondo effect and RKKY interaction. And when these two energy scales competing, I mean, when they cross here, you may find a quantum critical point, okay? And this phase diagram is the temperature, the transition temperature of the system, and the exchange integral between conduction electrons and localized moments, okay? And this quantity here can be changed by pressure effects, chemical pressure, or applied pressure, and magnetic field, whatever. So you can make a phase diagram like that, okay? And here is the transition temperature, and here is the quantum critical point. So the quantum critical point occurs at very low temperature when the thermal fluctuations are neglected, okay? In my system, is this system here. It's a ferromagnetic system below 7.5 K, okay? And it has a gamma, which is not very big. It's not a heavy fermion, actually, but it's a bit higher than for normal metals already. And the other side of the study I did a study with introduction of iron in this material here. So the parent compounds are this and this, no? It's much better. And this system is non-magnetic and is already a heavy fermion with a very high value of gamma, okay, of Sommerfeld constant. And then in my work, I made the phase diagram of this system, showing that doping with iron, the cerium, ruthenium-2, and germanium-2, we go from a magnetic system, ferromagnetic system, through an antiferromagnetism, and go to a quantum critical point, okay? And here is just an example. I will show you this picture again. And you see if you stop in 0.8 or 0.9 here of iron, with, 90%, you can see that this system is already in the quantum critical point. This is the signature of a quantum critical point. The resistivity is linear with the temperature at low temperatures, which is not common in normal metals. In normal metals, you see a quadratic behavior. And if you apply pressure, you go from the quantum critical point to this side, which is the Fermi-liquid behavior already. So we can tune the quantum critical point to the Fermi-liquid region just applying pressure. Just one example I'm showing to you. This is another. This is our another phase diagram, which is published somewhere. That is also a kind of chemical pressure in the same kind of material that also goes through a quantum critical point doping with silicon. Okay, what we use in CBPF in general is pressure. We have 3 kinds of pressure cells. We can use normal clamp cells. So here I put more or less the range of pressure we use. And also we can make experiment with diamond envy cell. Here we want to show some facilities, not for Mossbauer, okay, for the technique I use, which is resistivity. So we have a cryocoolers, not only one. We have a system that can go down to 100 milli-K, which is an adiabatic, uses adiabatic magnetic refrigeration. And this is the stick that goes inside this liquid helium cryostat. So we can make experiments with the pressure and resistivity at very low temperatures. Unfortunately, we cannot do Mossbauer at low temperatures, as Litterst is missing in his work. And these are all the facilities we have. And we have a Montana system for Mossbauer as a function of temperature. I think it can go from 4K, Dalbert, I remember, it's 4K up to 300K, I guess. So we can make Mossbauer experiments in this. And we also have Oxford cryostat with a 10 Tesla magnet. And we are trying to revive this cryostat. It has some problems, but we are going to invest a little bit so we can make Mossbauer with applied field again. So again, I want to show you 2 kinds of work we have done with pressure cells in CBPF. This went to very high pressures. Okay, so it's in gigapascal here, so it's 108 kilobars and 160 kilobars in Cerium platinum and ytterbium iron 2 germanium 2. And this is just an example of the phase diagram we can obtain in this kind of system. Okay, we have many other examples. So I want to talk about the work we did in the beginning that was with iron doping the cerium, ruthenium 2, and germanium 2. And I did the complete doping, measuring resistivity, and you see that the material goes from a ferromagnetic to a a non-magnetic system and passing through a quantum critical point, as I told you. And this system is magnetic, not heavy fermion, but it becomes a heavy fermion as you dope with iron. Okay, this again is the very nice example. Somebody told me in a conference that is a textbook example, and this is the crystal structure that is thorium chromium 2, silicon 2, and you have a ruthenium here, and you have a tetrahedral of germanium around, and another tetrahedral of cerium around. It's very important to tell you that the doping of iron here, it's nice because iron, you can make Mossbauer spectroscopy, and iron is electronic with ruthenium, so we don't expect much changes in the band structure, and you expect that the main effect of the doping is a kind of pressure, chemical pressure, okay? And iron in this material, as ruthenium, as any transition metal you put here, none of them carries magnetic moment. This is very important to keep in mind, that iron here doesn't carry magnetic moment. It is very well known in this kind of structure, okay? So because we had iron in our system, we did some Mossbauer spectroscopy, and just to start this work in Mossbauer, I never used it, so it was my first attempt. And you cannot see here because it's an old plot. I could not find the data to fix this, but there is a line here that is fitting this spectra. But in the beginning, we could not understand very well. So Elisa was very important in this work, of course, because she interpreted this as a B hyperfine field transferred for the cerium iron, the cerium ions, because cerium is 4F, so cerium has magnetic moment. So the B hyperfine field that you see here is transferred from cerium moment, and it has the same order of magnitude of the quadrupolar moment. And though we had this idea that we had to use B hyperfine and quadrupole with the same order of magnitude, we could not go to a conclusion by this first experiment we did. So Dauber had started his PhD by that time, and we were already working with boron carbides, which was a boom in the field of condensed matter, this kind of materials. And Dauber did a nice work in many of them. And I put one example here that is terbium. Dauber has doped with 1% of iron, this terbium nickel boron 2 carbon, and he found the same kind of asymmetry of the spectra as a function of temperature. And I don't want to go in details. I put the reference here, but he could find that this is a combination of a quadrupole splitting with a B hyperfine field of the same order of magnitude, and he could even find a very weak magnetism, which is a perpendicular component of the B hyperfine field in projected in the VZZ component in the plane, and the main component is parallel to the VZZ, and but this small component is fluctuating fast. He did Mossbauer, he did the MISR, he did the neutron diffraction, and all of them were going to the same direction. And he could, and after some temperature, you could see the system going to have a perfect alignment with the VZZ. Is the gradient, is the field gradient for the system, okay? And he also found the same thing in the Holmio, and in the Holmio was very nice system because it was superconducting, and when the system is a bit canted in a range of temperature, it introduces pair breaking field in the system, and the system becoming normal. And after some temperature, it goes down again. It means it becomes superconductor again. So you have here a reentrant behavior where this canting of the moments generate a pair breaking field in this system. It is very nice work. So again, we went to our system, to my system, and I did the fittings, and we found this problem here for the range of where the material is magnetic. We found this discrepancy in the quadrupolar moment. We could not understand by the time. We could obtain the B hyperfine. Another thing is very important to say that it's not possible to fit these materials if you don't take into account the angle between the B hyperfine and the VZZ, which is the what? Electric field gradient. I could not remember this name. So it's very important to take into account the complete Hamiltonian to fit this material. Anyhow, you got this difference in the quadrupolar splitting, which we will expect to be the same at low temperatures. And we could not understand by the time. And we did another sample, another material. We tested again, and we had the same problem. You see, we did the material, and now we just put some small amount of iron to study the pure material. And we did all the fittings going slowly in temperature. We had the same fitting. And nobody has come to a conclusion here. And so I did an experiment in cyclotron, trying to see if there is some shrink or some anomaly in the crystal structure. And we did this as a function of temperature, and working with Granado in LNLS. We came to the conclusion that the volume variation was only 0.5%. No anomalies were found in the lines, no difference in the lines, and this is only thermal contraction, normal thermal contraction of the lattice. So we thought, okay, it's not a problem of lattice contraction or change in this electric field gradient, okay? And now I'm working with Mariela. Mariela had the idea to make the fittings, keeping the quadrupole splitting as it should be, constant, and she introduced two subspectra. I just want to call your attention for this line here, which is maybe some small impurity in this sample, or it's maybe some iron that is going to germanium site, which is also known for this kind of materials. Sometimes when you dope with iron prefers to be in ruthenium and germanium site, and then there may be some iron going to germanium site, and it's not bothering too much the rest of fittings, okay? So again, we did the fittings, and she's using two components here to fit this spectra, okay? again using an angle between the hyperfine field and the electric field gradient. And she could fit very well this spectra this time. And we are now discussing what it could be. You see, she got the quadrupole splitting with no anomaly and the hyperfine field, which is a bit higher. And we are discussing that these two components, it's maybe the B hyperfine field that is parallel to VZZ, a component parallel to VZZ, and another component that is perpendicular to VZZ. And this component that is perpendicular to VZZ is 2 times fold. You may have two components that is perpendicular to VZZ, and that's why you have one bigger than the other. Okay, the area, no? And so in this case, you could ask. So then we should make the fitting using 3 components, but probably 2 components is enough, because you have 1 parallel and 2 perpendicular to electric field gradient. So these 2 components that is perpendicular is, let's say, equivalent. Okay, so we are finishing these discussions. Probably what I'm going to try is to improve this material to be sure that this line may disappear, so it will not bother our system. And then here is the explanation of the subspectra. I forgot to show you. And it's not easy to see this axis because the symmetry here is tetragonal and it's not very easy. So we still don't have the full analysis of this. And this is the final fittings compared with what we had before. So this nice anomaly, which I liked very much in the beginning, disappeared. And I want to go to the conclusions. And it's very important to know that iron really doesn't carry magnetic moment in this doping. The magnetic field on iron atoms is only transferred from cerium atoms. The Mossel spectra is a result of hyperfine field and a quadrupole interaction of the same order of magnitude. And the Mossel spectra with low doping of iron could be understood in terms of a combination of 3 subspectra due to the projection of a big hyperfine field on the VZZ components. Thank you very much.
Okay, Magda, thank you very much for a nice talk. And you brought some question, and maybe some friend can help us to
of course
to
that
think
would
about.
be great.
So time is open for question. Yeah, Julian, please.
Thank you, Magda, for your very nice talk. It's a very interesting system, and I think the approach that you made, that doing this systematic iron and substitution, can bring you a lot of nice and interesting information. I have 2 questions about the spectra that you showed with this new model. Well, one is just a supposition. I think that you probably are thinking about doing most power spectra with external magnetic fields.
Yes, we will try actually before we come here, but the cryostat was off for a long time, I think more than 5 years, since we didn't have helium. Now we have helium, and we tried 2 times to fill up the cryostat, but it has a hole somewhere.
Because I think that the most power spectra with external
Yes,
fields
that's
will
what we
help you a lot.
Of course,
with
yes.
distinguishing these
Yes,
magnetic
yes.
sites. And the other question was about that third small component that you show, that I see that the area increases with temperature.
Yes,
so maybe it's an
maybe.
it's another site, I don't know.
I want to get rid of this phase because this is a new sample I did for my student 2 years ago. And I think I was not careful enough. I didn't do heat treatment because it was a very simple work for scientific initiation, and then Mariela came to the work, and we were trying to at least understand how to fit this. So my next attempt is to really improve the material and do Mossbauer with applied field.
Just came another question. Is this sample sensitive to air? Because then
no.
Well, then because if it were somehow sensitive to air, then
I
it would
think
be expected that some.
It's just, I think no. No, these are some different samples.
But do you still have the sample, the old sample?
No. I don't keep things. I just trash every year. I trash everything.
It was a long time ago, Magda. It was a long time ago.
Yes. I have a problem with keeping things. I don't like it.
Me too. Viu, Rafinha? A Magda concorda, please.
Thank you for your talk, very nice. And I assume these samples are polycrystalline samples.
Polycrystalline samples,
Would it
yes.
help to study single crystal samples?
Yes, it would help a lot if I could find somebody to make it for me with iron 57. Yes, and I have a iron 57 a little bit, so. Yes, this is very nice sample to grow because congruent melting, and it's very easy growing material, no problem.
I see. And I assume, I'm sorry, I assume that iron is iron 2 plus.
Iron 2 plus, yes. But you can, when you do, for instance, I have prepared, I measure this with Edison sometime, and I prepared the sample with 1% of iron. And it was nice, Edson. We did a very, but we could not find the best fitting anyway. So, and I put iron 57, the spectra were very good. And, but this spectra is not easy to fit. Actually, you can fit with, if you increase the width of the lines. If you increase the width of the lines and put hyperfine field, you fit. If you increase the quadrupole splitting, as I showed you before, when it seems to have an anomaly, I mean, we feel that if you increase the quadrupole, you fit. So we increase the quadrupole fit, you can fit. If you, it's anyhow you have to put angle in the fit. Yeah. You know, it's very important to put the angle in the fit, otherwise it doesn't fit. So you really have to choose what is the best fit for this material, because it's all the parameters, they are very sensitive, they are very much in the same range, they are competing very closely, so it's difficult to see. Yes, single crystal could be, but you know, this material, it could help, but this material is so easy, it's congruent melting. And the only thing I didn't do for this sample was heat treatment. That helps to have homogenization of the material. So that's my fault. But anyhow, it helped to understand better what kind of fitting we should do.
Okay. Álvaro.
Magda, thank you very much for your presentation. I have two questions. The first one is the iron content that you present in your work is a nominal content, or did you measure this iron content by chemical techniques, other technique?
Well, you know, we are very experienced in preparing these materials, you know. And in the beginning of my work, my PhD thesis, I did many experiments trying just to check on these concentrations. And they were all very good. I still have the data somewhere in CBPF. So I'm very confident with this kind of sample preparation.
Thank you. And the other question is a curiosity only. Did you take Mossbauer spectrum without iron doping in order to see any contamination of the precursor?
Yes, we did with ruthenium, I remember, but I should look up for this data somewhere. But we use very pure elements to make these materials, okay? We use the best elements you can buy in Alpha ESA, okay? And the contents of impurity, I think, is much below the possibility of detection of the technique, I think.
So thank you for the talk. And of course, I agree that it's necessary to apply, it would be interesting to apply internal magnetic field, but why not maybe to polarize the source?
Well,
because usually when you have something which is not resolved, maybe by polarization of the source, it could make some simplification on your spectrum. I do not claim that it might be easy, but it might be also a possibility.
Okay, it's noted. I think we can discuss this with Dauber and
So
Mariella later.
And you have to look to the papers of his name, Jimanski, Krzysztof Jimanski in Poland, because he worked on this, and instead to have one line, he could have, or 6 lines, he could have only 3 lines. And maybe a possibility also to do synchrotron.
Yes, that would be great, yeah. Now, we have to think about.
Okay, thank you very much, Magda.
Okay.
Magda.
Okay.
So now it's time for Alisson. He's going to talk about effect of cutting fluids and storage time and the structure and magnetic properties of synthesized niobium iron boron magnets. Machining is legally.
Okay. Can you hear me? Good morning. Actually, good afternoon. And first of all, I thank you very much for the LACAME committee, for Edson and José Rafael to invite me, and it's an honor to be here, and after just 2 years of pandemic. So today I presented these 2 kinds of work, and I really emphasize this more related with Mossbauer effect, with this this effect with recycling neodymium iron boron magnets, permanent magnets. Is interesting market, and we can find everywhere these permanent magnets. And after I discuss briefly this kind of the other subject, but we can in the future use this kind of results to improve this effect in using this neodymium iron boron targets in the magnetic sputtering and the growth multi-layers of permanent magnets. So, like the other professor discussed here in the last days, You can find these permanent magnets everywhere. Some kinds of examples, like in these permanent magnets, these motors with like 1 kilogram of course, I discussed these neodymium iron boron magnets, but this stoichiometry always have other kind of elements: praseodymium, dysprosium, terbium, cobalt, and so on. Yeah, this is more difficult to study this kind of a larger of elements in these permanent magnets. And today we find these electric vehicles or hybrid vehicles, and the wind turbines with the renewable energy. It's sorry because it is more delayed, this kind of kilograms, but in this wind turbines you can find like 300 kilograms per megawatts, and this kind of this other machine like electric bike and the other sensors. This, I think the main problem is that China dominates this market, and the China have the resources, the many kind of the other elements. We see here that China not only dominate this market, but the mining, the separation process, the refinement, and the magnet manufacturing, or the China is everywhere. And we need this kind of materials. We can buy this kind of permanent with the China, and this prices increase with. Yeah, it's like a monopoly market. We can see here, and this other picture here, we discussed like the importance of the clean energy and the supply risk. And you can see here this neodymium, dysprosium, and the terbium. This is the main element in finding the permanent magnets, and the supply is almost dominated by China. And so why use these recycling routes or the chemical routes recycling, and why use this kind of the other routes, like we can start with this hard earth permanent magnets. We can go on in this diagram, but always we have this. Why we use these recycled alloys? So we can reuse these alloys and to start the other experiments, like I discussed after, this target element with this produce these multi-layers permanent magnets. And the first work we are doing this in Minas Gerais in CD10. This is a picture of this chain of the hard earth permanent magnets, not only the neodymium boron, neodymium iron boron. Here's the risk supply, like this neodymium, terbium, and the raw materials, and it goes on to produce these permanent magnet shapes. We can see how the different shapes, the different applications, and the main problem is this kind of here. We see we always need to cut this kind of permanent magnet or polish or yes, we always need to cut these permanent magnets and so on, test these magnet properties. So you can find these shapes and dimensions, the length, the width, and in this region here, we almost have this 30 ratio loss, and this residue with the cut machine, we can use this this residue, this powder residue with the cut machine, and come back to this root and produce new magnets or this recycled magnets. So this is some example, but it is not the diamond cut saw, but we can see here it's more the aluminum polisher. We need always this kind of, sorry, it's small, but we need always some fluid because this friction causes some damage for this permanent magnet, this heat up these permanent magnets, and we always need some fluid. And in this work is study two kinds. We started with water fluid, this common use, and the other is the synthetic oil fluid. After the machine produces this residue, this is like this sludgy residue. We need to the other process to clean, to ultrasonic clean with alcohol and so on. For example, this is summarize of the methodology. This is kind of this grinding wheel machine we use to cut, to polish this higher permanent magnet, and we discuss we study with most spectrals, X-ray, and the magnetometry. And like I say, we study with water, cut fluids, and synthetic oil, and with different storage times, and 30 days after 9 days. And this is in storage in the synthetic oil. The first result here, the X-ray diffraction, this partly shows this residue for the grinding machine almost have 96 of the 214 phase of this permanent magnet. This is very important, this high purity of this phase, because we need this residue to reuse in this chemical route to produce the new permanent magnets. And we also find in this hydroxide neodymium, and with this oil, this oils synthetic fluid, and this kind of always in these grain boundaries that have more probably reactions and the kinds of oxidation states, and this kind of hydroxide neodymium arises with is more problems arising in the grain boundary. And the study with this multiple spectra. Here, like the professor say, we have the structure of the 214 phase neodymium iron boron. We have these 6 non-equivalent sites of iron, and of course each one is yours hyperfine parameters. And so why is this defeat? So the next slide, and we use the multiple spectra, and we can find here these 6 states, and also we find this alpha iron in this powder, this sludge, and also we find in the other ferrohydride phase, and the other also with this when you cut or with your some literature, you find always with this friction of this machine, of this cut diamond saw or alumina polish, we produce some pressure or friction, and this other phase here, it's this kind of distortion in this lattice parameter, and we find this better fit with this simulate most Bauer spectra. So this is site of the non-equivalent size of iron, and the other phase with the distortion, crystal structure, and we agree some values of this hyperthin magnetic field. It's okay. I can say in the average, like many China articles and so on. It's almost 27 Tesla. And okay, this is the other parameters with the distortion of the structure of the neodymium iron boron. It's more, sorry, it's less magnetic hyperthin field, and okay, and this is with the oil synthetic fluid. Like when you fit here, we can find this 80 phase with the 240 phase of neodymium iron boron, and the other with distortion structure, and the ferrite, the alpha iron, and the other cations. And if you cut the semi permanent magnet, the semi grade of permanent magnet, they are significant reduce of this important phase of neodymium iron boron, and the other parameters is almost same, but here we not see a very high increase of the alpha iron phase in this spectrum. And okay, why we study with this magnetic hysteresis loops? We can find here we have a decrease of with water to almost 100 mol by gram to 70. And when we measure with this along with fluid, why we keep this permanent magnet storage in oil synthetic fluid, we almost find this 90 days there is no significant change in these parameters. So this is the other study we have done in this CD10. I briefly discussed this because I mostly discussed with the composition of the neodymium iron boron permanent magnets, and why study dysprosium, or why use dysprosium? Because dysprosium, okay, dysprosium have almost increased the Curie temperature and the phase transition, the ferromagnetic transition, and we fabricate grown this film structure. We've increased the dysprosium interfaces, and we can start this 3 samples we are doing in this magnetic sputtering, and this was done in high temperature and increased the diffusion of the dysprosium inside of the neodymium magnetic layer. And with this X-ray, we don't see many change, but what is important to show here, it's a magnetic measure. This fork magnetic measure, we can extract this different phases inside this kind of multi-layer structure. And it's more important is show here with we have 2 layers. We have kind of this structure show us 2 kind of soft layer in these states when we measure this permanent magnet in magnetic field apply in plane of the multilayer. And here we found almost this kind of boomerang shape, and this is almost 3,000 magnetic cohesive field. And there is the importance of study this interdiffusion process. And this is the last result I can show for you. And I finish here, and I thank you for your attention and the financial supports and my collaborators in UFMG and the CDTN. Thank you very much.
Thank you, Alisson, for nice talk. Is there any question? Of course. My friend.
So thank you for this interesting topic. Could you show us the spectra of neodymium iron boron?
Yes.
Yeah. Okay. Could you explain why the global lines are so large? Because typically, at room temperature, between each line, we go to the baseline.
Yeah.
Is it a problem of disorder, problem of size, problem of grain boundaries, problem? Do you have an idea?
We actually don't show here. We try to, because we extract this powder in the machine. These are a broad distribution of grain sizes, and maybe there is a effect. And with this cut machine, we don't have this, like I say, a straight distribution of grain size. We have a broad grain size.
Any other question? So, Alisson, just one small comment. So the first part of your talk, it's very nice because if I understood correct, you are taking the residues and you are trying to use or to see what is going on with the residue. So probably one of the problems that Ganesh has asked you, it's a result of the friction and you have internal stress and stuff like that. So that's very, very clear, very nice. And the second part of your talk, so you are trying to prepare multi-layer with dysprosium. So as Ligia tell us in the beginning, so Earth is every time much more expensive.
Yes.
Because they are controlling quite well. So, and then the TC of the permanent magnets, they are already above the room temperature. Why should you use dysprosium if you have already the high temperature feature that you need for the magnet, for the permanent magnet?
Okay.
You understand my question?
Yes, I understand. Maybe I run in this discussion. Sorry. So me here. Okay. Of course, dysprosium is very expensive. We are trying to use the other high earth elements like cerium and lanthanum, but I started with this dysprosium because they have many literates and results with the China, and the high content of dysprosium you can use in these other kind of applications. Of course we have this room temperature here, almost here. But the other application need more high temperature TC magnetic or permanent magnets, and like this high performance motor or generators. We need to increase the this ITC.
Okay, I have one, I guess, sort of a question. So the idea is if you could reuse the sludge, that of course would be better. But I mean, are people, I'm not saying you are, but are people, they must be working on recovering the neodymium, because you don't care about the iron or the boron anyway, but it's difficult to recover the neodymium from the sludge.
Oh, okay. So yes, I understand. Is we take this sludge, we do some chemical roots, and we obtain powder. And the next, we have collaborate with in the south of Brazil, produce a target or if magnetic elements or this target, and reuse in this sputtering, for then produce a fin in magnetic sputtering, and after recover with disposal.
Right. So it is possible to recover the neodymium for future use.
Yes.
Yeah,
yes.
yeah.
The only thing that he said is, so he needs that powder, and he can build
Another permanent.
target to be used in the sputtering system, so to produce thin films, for example.
Oh, I see. So it's not even for making more magnets, even. No,
Yeah, yes.
It's just it's like a mine of.
Yeah.
This is a mine source instead
Yeah,
of in
it's
the
a
ground in China. Okay, thanks. I see. The other, then I just have a comment, and it may not be useful, but it is possible to do dysprosium Mossbauer, and Volker Schünemann in Germany is doing that. Maybe somebody here knows of doing it. I don't know, but it's, yeah. But he's working on molecular magnets, so it's whether that's used. They must be using it in these other things. He's working only on molecular systems. That's all I know about. But I'm sure if it's possible and be useful to do the dysprosium Mossbauer also.
It's interesting comment. Thank you.
Gadolinium André has done, but probably he also can do dysprosium. I'm sure. No.
Thank you, Alisson, for your talk. You did observe some phase separation in the residual. Is that right, in the sludge? A phase separation.
Yeah, I don't show here. We measure with the fork measure this sorry, like this. We do this fork measure with the sludge.
No, there is another picture where you showed us the fractions of.
Here.
Yeah. No, before. Yes.
Okay.
See that Mossbauer spectrum, you have showed two phases, or the classical phase plus 11% of neodymium iron boron, and etc. My question is, did you characterize the resulting piece, or just the sludge?
Yeah, only the sludge.
Only the sludge.
Yeah, only the sludge.
Because it's important to see if the resulting piece resulted good or not. I don't know.
Sorry, we characterize the sludge with the powder, and I don't show here, but we do this fluorescence measure, and it's almost the same stoichiometry.
Okay, thank you.
Okay, guys, I think that it's time to stop. At least let's thank Alisson, all the speaker from the morning. I have two announcements.